Hey, Astro friends. So I was just talking to one of you about problem set one. It's not really problem set one, assignment one. And I really think it went well for everybody, but there was a good question that I got about how to kind of tie all of the loose ends together and make sure we really understand what's going on with drawing these geodesics in Krustal's Sakari's coordinates, especially what I meant by playing around with the inside solution to see if we can get them to match up. So I decided to record a quick little video lecture. I would love some feedback since everybody was real excited about more of these things. So I hope you watch it and then let me know what you thought as soon as you do. Thanks. Okay, so this is the Mathematica document that I'm posting on Moodle along with this video. It's right underneath it. So feel free to open it up and play along if you'd like. It'll obviously have the output with it because I'm going to post it after I'm done recording this video, not before, as not to break causality or anything like that. So I'm going to use a lot of structures that we've seen before, but I'm also going to use a couple of new structures because I figure since I'm making a video, I might as well give you some advice on how to do some of this Mathematica-ing and extend some of your skills in that way. I've also tried to comment this a little bit as I wrote it, so that way you can look back at it and use it. So I have set up here a shell of the operations that I'd like to do. So the first thing, as always, is I set the directory and I load great.m because I'm going to be using it to calculate Christoffel coefficients that I need in order to solve the geodesic equation. And to remind you, the problem in BASIC here is that we wanted to see what do geodesics look like in Kruskal's-Sakari's coordinates, right? And the advice that I gave on the last assignment number one, was to solve the geodesic equation in Schwarzschild coordinates and then translate that into Kruskal's-Sakari's coordinates before you plot it. Okay, and so the next thing I'm going to do is I'm going to load that metric, and I'm using these great units where r is in units of the Schwarzschild radius and t is in units where c is equal to 1. And I'm also I'm storing the metric in metric, and I'm storing the coordinates in this array called x's. I'm also going to generate my Christoffel coefficients just using great.m. I've mentioned to some of you, and it's worth showing here, that when I'm calculating all of my equations of motion, that is, when I'm calculating all four of the geodesic equations here, I'm using a table, and that's going to go over this index gamma, right, which tells me that I have four different equations, right? So table replaces gamma 1, 2, 3, 4, which is really 0, 1, 2, 3, but a table is a set of equations. And on the right-hand side, I then have a sum over my Christoffel coefficients times derivatives of two coordinates, right? But that right-hand side is actually a sum over alpha and beta. So if you look back at the geodesic equation, right, what you see on the right-hand side is minus Christoffel coefficient, dx alpha d tau, dx beta d tau. But that's implicitly summed over alpha and beta. But then there are four of them, one for each value of gamma. And these four geodesic equations that come out of this look a heck of a lot like the ones that almost everybody, I think everybody used in this problem set, because I think everybody had really nice geodesic equations from assignment one. I'm also going to try to automate a little bit this idea of the initial condition, because I think the most common mistake that I saw was the inside geodesics were solved for not really geodesics because the initial conditions were bad. That is, the initial conditions didn't satisfy what we know about world lines, meaning that u mu is equal to -1, that u dot u is equal to -1. And so what we need to do is to solve that, we need to actually satisfy this constraint, right? U upstairs mu, U downstairs mu is really G mu nu, U nu. That's a fun thing to say, equals -1. And so I'm going to call all the individual components of this, T prime, R prime, theta prime, phi prime. And then while I'm at it, I'm also just going to set up a little sort of initial condition vector, which I'm going to call x naught. And actually, as I think about this, I don't think I ever used that as I was trying this notebook out before I showed it to you. But I have all of my primes, t, r, theta, phi, and then I have this expression that came out of looking at that, that constraint, right? So the initial condition constraint, that's what I'm calling this equation, is a sum over alpha and beta of g alpha beta, x alpha, or u alpha, u beta, right? That's what this expression means. And that has to be then equal to -1. And so this is really the algebraic condition that I always have to ensure that my initial conditions satisfy in order to be a proper geodesic. So now I need to do a little bit more housekeeping or something like that. Well, actually, so I have an example, sorry, before we go on to housekeeping. So a way that you can use this, so if I wanted to solve the initial condition constraint to give me t prime, all I have to do is say solve this equation, IC constraint, for t prime, given, and I have to always say what 3 of them are, right? I can't solve for t prime unless I know r prime, theta prime, and phi prime, right? That's the idea here, is that if you know 3 of them, you can get the 4th one. And you can see that the output of this solve is a list of lists, right? It's a one-dimensional list that has two solutions in it, which are replacement operators that say t prime can either be minus this combination of stuff or this combination of stuff. Now, you'll also note in here there's that r of tau, right? And so when I actually go to use this, I'm going to have to make sure that I also say what r of 0 is, right? This is something that we're going to have to, this is something that's going to be important for really setting those initial conditions. Okay, the next thing I want to do is functions that are going to be useful for me. So I'm using Carroll's notation, where I'm using big T and big R to represent the two Kruskal-Zachary's coordinates, T outside and R outside. And on the right-hand side, I have the square, this is the definitions, and then I have a similar set of definitions for what it looks like on the inside. Then I just want to create. I want to create a background, right? When I plot my geodesics so that it's useful, I'm going to use. I use this little bit of code here, and this is similar to what I gave out in the problem set. This little code here just gives me a grid, right, where lines of constant r are red, lines of constant t are blue, right? And I can see if I look way out towards the right, things start to look like a regular old Minkowski space. But then as I move up this diagram, I cross the Schwarzschild radius, right? The old event horizon, where all the lines of constant t bunch up. And then when I get inside the black hole, still moving upwards, I'm forced now to cross lines of constant r, right? In order to move upward inside the black hole, I have to cross red lines. I actually don't necessarily have to cross blue lines, but I always have to cross red lines. Okay, so this is just going to allow us to visualize what those geodesics look like. And you should look back on the video that I made with Allegra last week, where I tried to sketch this out by hand, because this hopefully looks a lot like that. And in that video, we by hand plotted what some geodesics should look like, and now we'll find out what the actual solutions are. Okay, so to go over how I'm going to generate the geodesics, I'm going to choose initial positions, right? So I'm going to say initially r is 1.2, then of course that's 1.2 Schwarzschild radii, initial t is 0, initial r prime is 0, so we're going to be at rest. I'm going to use my solve command to give me my, to figure out what my constraints are. To make this maybe a little bit more transparent, why don't I take this part of the command and I'll do it separately so that you can see what the output of this solve looks like for this particular situation. But I'm going to replace r prime with 0, theta prime with 0, phi prime with 0, and then I'm going to set the initial r to be the initial r, right? I'm then going to store that in this initial t prime, so that way I know where my, so that's going to go together with these top 3 to give me my full set of initial derivatives. And then I'm going to generate my system of equations, okay? And this is what's going to go into NDSolve. The first thing that goes in are the 4 geodesic equations that we had above. Then what are my initial R and initial T, my initial R prime and my initial T prime, and then the angular components here I put down explicitly, but many of you didn't need to and didn't solve for those when you turned in your problem set. Then the big game happens. I'm going to run ND solve to get out my solution, and the two functions that I'm interested in are T and R. Okay. Then I'm going to get out those two functions, R and T, and I'm going to solve them. I'm going to store remember the output of ND solve are instructions, so I'm going to store the actual interpolating functions as RRR and TTT, right? These are the parameterizations for the Schwarzschild coordinates, R and T. This part is fun, and I don't want to get too much into it, but basically, the output of the ND solve is a list of interpolating functions. And deep in those interpolating functions, which are really classes, objects of a class, there are the start time and finish time, right? So normally what we do is we just run it and then we copy and paste the start and finish time. But I want it to be fancy and automative. And so what I'm doing here is I'm actually extracting the start time and the finish time from the solution so that when I plot it, I can plot the parameterization here, right? So this is now the Kruskal-Zakkares R and T as a function of the Schwarzschild R and T from tau equals start to tau equals stop, and then the plot range and the aspect ratio, and then my geodesic is going to be black and thick. And then because I wanted to put it on top of that grid, I'm going to show it as an output. So I know that this is going to work because I already tried it once. The first line that comes out is, of course, this thing that I added here, right? So what does the actual output of the constraint look like? Well, there are two different possibilities, right? It's a quadratic equation. So one of them is T prime of negative, one of them is T prime of positive. And I want the positive one, right? Because outside the black hole, I am moving through T in the positive direction. And therefore, my T prime, I want my T prime to be positive. And so when I'm actually pulling out the constraint, I've added this bracket 2, so that way I'm getting the instruction from the second entry of the T prime of the second entry, the second solution for T prime. And you'll see ND solve gave me this at tau equals 1.04, blah blah blah. But my start and finish have now extracted 0 and 1.04 automatically as my start and finish times. And this is what my geodesic looks like on this Kruskal-Zakkares coordinates, right? It's moving upwards and it stops exactly where I expect it to. So that process is really cool. I can move it around. I can move it to different radii. Let me move it to 1.3, right? And it moves out a little bit. You'll notice if you try to do it too far away, right? If I try to do it at 2, suddenly the geodesic, it goes off my screen here, right? The geodesic actually gets a lot longer because it takes just so much longer for that geodesic to hit the Schwarzschild radius. And so I'm going to keep it around 1.2 just so that it looks pretty on my diagram here. So inside, we have to be a little bit more careful, right? So here, I'm gonna start my geodesic somewhere inside the black hole with an initial R less than 1. I'm not actually gonna do it right at 1 because there's no definition of what the Schwarzschild T is. So I'm gonna go just inside the black hole. I'm gonna do it around 0.7. I'm also going to choose some non-zero value for the initial t. If I look up at this, that's because t equals 0 inside the black hole is actually the y-axis, right? And I want to move it to the right a little bit. So the further to the right, along these blue lines of constant t, I'm going to be able to move that geodesic away from the center of my Kruskal-Zakkares coordinates. And I'm also going to add an initial t prime. Now, this is one of those things you should play with and see what effect it has on the geodesic when you change the initial t prime. I want it to be negative because I want the geodesic to move to the left or leftward or upward and leftward in my inside region. And therefore, I really want to go to smaller values of t. Okay. And now I'm going to use my constraint to solve for r prime rather than t prime, right? Inside the black hole, inside the Schwarzschild radius, you have to cross lines of constant r. R prime cannot be 0 because as you move up on this diagram, you have to cross red lines, right? You can't not cross red lines and still be moving upward. And so that's the one that's hardest to find, and that's the one I'm going to solve for. I'm going to go ahead and actually evaluate it because I want you to see that this is a little bit harder for solve to get, right? So there are two different solutions. There's the unphysical one of 0.65 and the physical one of minus 0.65, but it gives it to me as a complex number, right? So when I store that as my initial r prime, I also have to go one step further when setting up my systems and only take the real part of initial r prime, right? I have to make sure that I'm only taking that real number because Mathematica isn't smart enough to say 0i is 0. It thinks 0i is 0-ish, right? And that's just not going to do it for plotting this solution. So ND solved, and the other thing I'm going to do, because I'm not starting, quote, at the beginning of the geodesic, I'm going to let my time, my tau, my proper time, run forward and backward by some ridiculous amount. And of course, as we see down here, right, it crashes at two different points, right? Because at some point in the past, the geodesic crossed the Schwarzschild radius, and at some point in the future, the geodesic is going to hit r equals 0, right? And so this is a finite amount of time, and this is a question that everybody asks in a grad level GR class. How long does it take after you cross the Schwarzschild radius before you hit the center of the black hole? Well, this answer is right here, right? This is how long the geodesic exists in proper time inside the black hole. Okay, start, stop. I'm gonna do that parametric plot exactly the same way, and bada bing! What a beautiful geodesic that starts at the Schwarzschild radius and ends at the center of the black hole, right? Ends at r equals 0. And you'll notice this is beautiful. It's moving upwards. The biggest mistake that I saw in the problem set was actually people taking the wrong solution here. So you can see if I change this to 1 and I take the positive r prime value, actually that one looks pretty good too. It's just on the wrong side of the black hole. The most common problem that I saw was when was in finding these initial conditions and not solving for r prime correctly. And what happens is you end up on a space-like path, right? And that space-like path is a solution to the geodesic equations, but it's not a geodesic. It's a minimum of proper time rather than a maximum of proper time, and the variational principle gives you a path, but that path is actually not physical. And so I get this path here, and that looks great. So the final challenge, of course, was, well, can we match them? So what I'm going to do is I'm going to repeat exactly that calculation we did before, but now I'm going to show both of the geodesics on the same plot. Now, of course, here, my initial time was small, and that tells me that how far away from the center is my inside geodesic. I want that time actually to be much larger, right, so that I move this internal geodesic more over to the right. So the first thing I'm going to try is I'm going to change my initial t from 0.5 to, say, 2.1. I don't know why I chose 2.1. Not big enough. Let me change it to 5. Too big. Isn't this fun? Let me change it to 4. Okay. And that also seems a little bit too big, so I will make it. I'll make it 3, and then I'll try to change another parameter. Oh my goodness! Actually, that looks almost spectacular. It's still a little discontinuous, right? And so if I look at it, what I really want is I want it to be moving faster in time, or I shouldn't say faster in time. I want it to cross more lines of constant t. So I'm going to come up here, and I'm going to take my initial t prime, and I'm going to make it a little bit bigger. Okay. And now the slope looks better, but it's moved to the right. So I'm going to come back here and play. Maybe I'll make this 0.9 and make this, let's see, was it too far? It was too far to the right. So I have to make this number a little bit smaller, maybe 2.7, right? And as I'm playing with this, you can see that things are happening, right? The solutions are matching up. And it doesn't take too long, once, of course, we have a geodesic that we can trust, right? to try to come up with some geodesic now that looks pretty damn continuous, right? And actually, I'm going to stop there because I am proud of myself for creating a nearly continuous geodesic across that event horizon. And this looks a heck of a lot too like the geodesics that Allegra and I wrote down together before. Okay, this turned out to be a little longer than I planned, but hopefully it was interesting. Again, please let me know what you thought of it. Thanks.